This week we'll begin our final lecture, which is on global climate change. So just to summarize this, we talked about in the very beginning of the class, but to refresh your memory, what is climate compared to what we probably talk about more often, which is weather? So weather then is the day-to-day state of affairs. So the minute to minute when you go outside, what are the variations that you're going to see from morning till evening, or as it says, from minutes to weeks. And that's going to be in a combination of the outside temperature, the humidity, the precipitation, so the rain or snow, the visibility, meaning, is it cloudy or is it not, and then the wind direction. So climate then would be the state of the atmosphere over a long period of time. So we're typically talking about a 30-year time span. That's usually the boundaries that we use for climate averages. Although it could be a longer period of time, we could talk about it as centuries or millennia. It will include all statistical weather information, including weather extremes. So as it says in the slide, climate is what you expect, weather is what you get. All right, so thinking about the seasons versus climate, right? So what does that mean? Is that weather or is that climate? So remember in this class, when we talk about climate, here in Florida, the summers are very hot and rainy and the winters are cool and dry. So the fluctuations that we see in weather that occur from year to year are still our weather. But however, if we were going to take all of our daily temperatures during the winter and the summer, so averaging them over a 30-year time span, that's climate. So as I have usually described this, it's the average weather, right? So seasons aren't necessarily climate, it's just a seasonal variation, which can fluctuate too depending on where you are. So when we talk about climate change, one thing that is a little bit confusing is we see this all the time. Well, I thought climate change was natural. Long-term climatic change is natural. So we've seen significant variations in the global climate over geologic time, right? So for example, you might have seen this in other classes talking about the ice ages. And this would be, for example, when we were talking about North America, where we had that frozen land bridge that allowed people to cross from the Siberia into North America and then populate the rest of the Americas, right? So it's an ice age. Or any of the times we had glacial periods. Then we have other periods where it was warmer, right? So during the medieval period, we had a warm period, and then another little ice age. And there has been some recent work that suggested that little ice age actually came about as a result of the Black Death. So if you know anything about the bubonic plague, it wiped out 1/3 of the population of Europe, and it was so many people that were removed that it actually caused a little ice age. We also saw a similar effect in North and South America, where so many people, the indigenous people, were wiped out by disease and warfare that it also caused a drop in temperature in North and South America. Those are honestly people-driven, right? Not necessarily natural climate change. But again, we just see natural variations in climate mainly as a result of things like the shape of the Earth's orbit, the tilt on its axis, and its gyration on its axis. So you can see that actually here. The Earth is going around the sun. Its orbit changes a little bit. This is also just due to the interaction of Earth with other planets because they also have gravity. So it is, drawing the Earth out of its orbit just a little bit. It's not a huge change, but it's enough to where it'll change the temperatures on the Earth. As you can see, it is tilted on its axis, so it will move a little bit on its axis. You can see that here, that's precession. And then you can see that the tilt will also fluctuate a little bit. So as it's rotating on its axis, precession, and then as its tilt fluctuates a little bit. There are also natural short-term climatic changes. We have looked at that a little bit when we talk about volcanoes. So when volcanoes erupt, we will see usually a cool down of the planet, because what's happening is particulate matter is now being released into the atmosphere, and so that produces a filtering effect which will keep the heat of the sun from reaching the Earth's surface. So it'll reduce the climate, the warming of the planet at that time. Sunspot activity, that's probably one that most people refer to when we talk about, well, aren't there natural fluctuations in climate? So yes, sometimes the sun has a little sunspot. So what that means is, as you might imagine, the surface of the sun is not evenly hot, right? So sometimes there's a little spot where it's a little hotter than other times, or it might be slightly a little bit cooler. So obviously that might change the climate of the planet. And then oceanic circulation. We discussed that when we talked about like Latin America, where we talked about El Nino, right? So those global ocean currents affecting the climate on the land. Those are all natural processes. So long-term climatic change and short-term climatic change dealing with natural processes. But there are human processes that are really what we're concerned about right now. And what that boils down to is the greenhouse effect. Just to take a little step back when we talk about greenhouse effect and make sure that we know what that is. In the atmosphere, there are certain gases that are functioning as an insulating barrier, which traps in infrared radiation. So the solar radiation is coming into the planet, and it gets emitted back into space. So it basically bounces off the surface of the Earth and goes back towards space. In our atmosphere are gases like carbon dioxide, nitrogen, methane, so on and so forth, that hold that heat in. That is a positive effect for our planet. If those gases were not there, we wouldn't have life on Earth because the planet would not be warm enough. So there you go. You can see that in this image, right? Most of the radiation that goes in from the sun is absorbed by the Earth's surface. Some of it gets reflected back out into space. And that's that process, that greenhouse effect. So the greenhouse effect overall is a natural process. It's just when it becomes excessive that we have a problem, right? So actually, I forgot about that. Can't go back. So one of the issues we have is that the buildup of those gases is what's keeping in the heat, right? So imagine that our atmosphere is like a blanket, right? And it's like a cool winter's evening, right? You need a blanket. Perfect. But now imagine that you've turned the heat on in your house and you have your blanket on, but you add another blanket and another blanket and another blanket and another blanket. And basically you down at the bottom of under all these blankets are starting to get really hot. You're starting to sweat. And that's basically what's going on with the planet, right? We've basically added a lot of insulating layers to the Earth's atmosphere, and that's mostly in the form of carbon dioxide. So carbon dioxide is an excellent heat absorber, and we've known about this for a really long time. We've known about the absorption capabilities of carbon dioxide since I think it's the 1800s. Now, actually, the most predictive of heat, the thing that absorbs heat the most, is actually water vapor. But water vapor changes pretty quickly. The amount of water vapor in the air will change within a few hours. Carbon dioxide, on the other hand, hangs out in the atmosphere for about 140 years. So that's why that one is such a problem. All right, so let's look at some of the evidence for global warming. So as it says on the slide, the 20th century was the warmest in 600 years. So during that time, the average surface temp rose over 1 degree Celsius during that century. Temperatures in the Arctic, unfortunately, have risen about 7 degrees Celsius since the 1950s. What that means, of course, is the loss of sea ice in the Arctic and the loss of our glaciers. So a couple things going on there. 1 degree Celsius doesn't seem like a lot. If you are someone who's not familiar with Celsius, if you're more of a Fahrenheit person, it's very simple to hop into Google and do a converter, and then you can see what that temperature change is. But just to talk about that a little bit more, thinking about this as a fever, right? So if you had a fever where, normally your temperature is 98 degrees Fahrenheit, and if you have a fever of 100, it's not a huge temperature change, except there's this long-term pattern of holding on to this fever. You're not going to feel very well. That's basically what's going on with our planet. And then thinking about in the Arctic, with that average temperature increase of 7 degrees, what that means is it's 7 degrees above the normal temperatures, right? So unfortunately, carbon dioxide actually tends to hang out at the poles. It tends to collect there, right? So if you've seen some of those NASA maps where it shows the hottest temperatures at the poles, the highest degree of temperature change, I should say, it's because the carbon dioxide tends to hang out there, right? Which is why we've seen actually an increase beyond the average increase at the poles. Oh, there we go. Perfect. So this is the global warming projections based on the 1960 to 1990 average and predicting for 2070 to 2100. Apologize. And as you can see, like really dark red up at the Arctic area. It's because our temperature increase is likely to be quite high there, right? And that's why, because it's where the carbon dioxide likes to hang out. So some of the things that have really concerned scientists is the human output of carbon dioxide. So as I said before, carbon dioxide is an excellent absorber of heat. So carbon dioxide absorbs that infrared radiation, that sunlight that's coming into our planet, right? And it absorbs it at a rate, typically when we talk about rates of absorption, we give carbon a rate of 1, which means that it's 100%, which is a little inaccurate, but in terms of like trying to explain that, we're going to go with 1, right? Whereas other gases that are in our atmosphere actually don't do that. That's why we don't think about things like nitrogen or oxygen, because they don't absorb infrared. Okay, but unfortunately, other gases like methane, as I said before, nitrous oxide, and ozone are absorbers of heat. All right, so thinking about that, like 1, that measurement of 1 for carbon dioxide as an absorber of heat, nitrogen and methane. So like methane is like 4 times an absorber. Nitrogen is like a 3 times absorber. So that is a huge problem. We're very lucky that actually that's not the gases that are most prevalent, right? But it's carbon dioxide. Okay, so taking a look at our graph that we have here on the slide. So we have starting from about 400,000 years ago until roughly today. So 0 is 1950. And we chose 1950 because that's when we start to see many more cars on the road. That's when the personal automobile starts to become more popular. All right. And for centuries, as it says, the atmospheric carbon has never been above this line. All right. So at about 300 parts per million in the atmosphere. As you can see, exponential growth above that line since 1950. So our current level, actually, I think the last thing I said, we're in the 440, 480 range. So we've even gone beyond where this map was, or this graph was a few years ago. So that's a concern, because we're basically adding this heat absorbing gas to the atmosphere. And since carbon dioxide doesn't leave the atmosphere very quickly, we're in trouble, right? That's going to increase the warming of the planet. So one of the effects we're seeing as a result of this increased warming of the planet is glacial loss. This is pretty stark when you look at pictures. There was a National Geographic photographer who documented some of these glaciers. His are the more recent ones. Obviously, he didn't do this one from 1913. But this is just comparing some of the glaciers globally. You can see this image from 1913. That glacier in 2012 is basically gone. This is from 1996, going till, 2009. So really not a huge time span. And again, huge loss of our glaciers. All right. And again, rising temperatures globally. And this is a result of excess carbon dioxide being put into the atmosphere. All right. And you can just watch the years change on this image. You can see, okay, some fluctuations in the temperature, but we start to climb and we start to climb and we start to climb. All right, so looking at that date in the upper right. And by 2017, as you can see, again, here you can see where that heat is just hanging out in the upper levels of the planet, right, in the poles. So how do scientists study climate change? How do we know all this, right? So just you don't have to take my word for it. There's data that scientists are using to collect this information. So the primary way that they're doing it is through the collection of ice cores and sediment cores. So you see that here, and these are sediment cores. And what they're looking for is, in terms of the ice, they're actually looking for trapped gas. So gas bubbles will be trapped in the ice. And that will tell us the carbon dioxide that was in the atmosphere at the time when that ice was created, right? And the sediment core, we're looking for soil respiration and overall sediment health. So if you didn't realize that, one of the largest absorbers of carbon dioxide is actually soil. So we want to keep it healthy, right? And that's kind of why we're examining the sediment to see what happened in the past. Then both of these things might be run through these types of equipment. So the mass spectrometer or the scanning electron microscope, which tells us the gas composition of those items. So these are two different ways that you can look at evidence for climate change. I'm not going to get into that for this, but you have the opportunity to look at those things. So one is dealing with the global ice that is still existent, as well as looking at the sea level rise. Right, so we're going to talk about some of those global effects of climate change, and that will get into this. I'm not going to spend a lot of time on that, but you're able to look around at this stuff. You shouldn't take my word for any of this. The evidence is out there. All right, the current state of climate change, right? So the global temperature has risen 1.8 degrees Fahrenheit since 1880. The current concentration is at 409 parts per million. Sea ice melting, right? Global sea level is currently rising at 3.2 millimeters per year, which doesn't sound like a lot, but that's because of why that's happening. So as it says, where is most of the incoming heat ending up? It's going into the oceans, right? So our oceans are actually where most of the heat currently is being absorbed, right? So this is also what's at this point contributed to sea level rise, because the water expands as it warms up. We've seen that happen. If any of you, wear rings in the summer, sometimes your hands are swollen and you got to take the rings off because your hands swell in the heat, right? So water will expand as it warms up. So that's called thermal expansion, as it says in the slide. So in order to fully understand this, I'm just going to do a little bit of science. So a little bit about water and the biogeochemistry of Earth. So water has some chemical properties that make it hold on to heat really well. So most substances will contract when they get colder and also get more dense, but water does not. You can actually see that on this slide. So there's our water molecule, probably the most famous molecule, H2O. And in cold water, you can see those water molecules are actually pretty dense. So if you were thinking about the ocean, our cool water that's not ice will be down at the bottom. Okay, that makes sense. Then the warm water will be floating above it. However, because of the chemical structure of our water molecule, basically acts like a little magnet, it will form this lattice structure which allows it to float. All right. That also allows it to absorb heat really well. So that's what we're looking at right here. So this is a comparison of our water molecule to sulfur dihydrogen, which is a similar chemical structure. And as you can see, this is our range at which our H2S will remain liquid. So only a 24-degree range will it remain liquid, whereas H2O will remain 100 degrees, will remain liquid for a 100-degree range. So then that means it's going to go into the ocean. The water will absorb all that heat, right? So as it says, and as I mentioned before, that CO2 is going to go into the atmosphere for a long time. It's about 140 years. So all the extra heat that this absorbs is going to go into the ocean, and it might stay even longer as it slowly sinks into the deeper ocean waters. So our current sea level rise is as a result of the thermal expansion of water. But at a certain point, what's going to happen, as it says on the slide, is our ice sheets will continue to melt. So as those ice sheets melt, they're adding to the water. So that's actually where scientists are most concerned. I mean, obviously we're concerned about the thermal expansion of water as well. But when the ice sheets start to melt, that's where we'll see a big jump in global sea level rise. So that's where we're mainly concerned. Kind of showing that same thing, that volume, thermal expansion of water. So as the temperature starts to increase, you can see the volume of water will also increase. So this is what we're talking about really, right? So our CO2 emissions, right, that we have, if we can stabilize our CO2 emissions, hopefully we can get some stabilization going on for this, right? And that's what we're hoping for. We want to stabilize the CO2 emissions, stabilize the temperatures. However, it's going to take millennia before we reach the equilibrium with the sea level rise due to the ice melting as well as thermal expansion. So as you can see, it's actually going to take 1,000 years or more for that to stabilize. And that's if we reduce emissions now, right? All right, so just a little bit more about the biogeochemistry of Earth. So I've mentioned nitrogen oxide as another greenhouse gas. So the nitrogen that we utilize is actually not what's in the atmosphere. Most animals cannot process it in the form that is in the atmosphere, which is nitrogen. All right, so what happens is, again, we need the soil to be alive to do this for us. It will get fixed by bacteria in the soil, right? And in the soil is the living component of the dirt, right? Sediment is the dead part. It's inert, okay? This does occur naturally, as you can see over here. So this is our natural nitrogen fixation. And when we say it's fixed, it becomes a form that it can be used. So you see that here, right? It becomes a nitrate, which is what gets absorbed by plants and also consumed by animals. All right, so the natural fixation, this is our level, but then we're seeing that rapidly increase as a result of fossil fuel combustion and synthetic fertilizers. All right, and why is that a concern? Because basically, again, it's killing the soil and it's contributing to our global atmospheric nitrogen oxide. And then that carbon cycle, again, I just wanted to show you this. Really, the carbon cycle, you're probably pretty much familiar with that. But you can see here where it is being absorbed by the ocean. So that's our carbon store, right? So the deep ocean as well as the ocean surface. It does also get absorbed by our soil, right? Again, we want to protect our soil. Also, plants, vegetation will absorb it. And eventually those will become our fossil fuels, but we're burning them at a faster rate than that's being absorbed. So how do we know some of this? It is a result of a scientist by the name of Keeling. He is in Hawaii, and he was monitoring atmospheric carbon since 1960, and he created what we call the Keeling curve. And what we've seen is basically just this exponential trend in increase. All right, so what are some of these climate change impacts? And we're going to go into each of these in more detail. All right, so let's talk about each of these in more detail. So in terms of overall weather change due to climate change, and I just want to take a moment to talk about climate change. When we say the words climate change, you might have in the past heard the words global warming. We started talking about it as climate change versus global warming because of these changes in weather patterns. So, we'd have things like that polar vortex happening, and people got very confused because there's a ton of snow, right? We're getting 10 feet of snow. How can that be if the planet is warming? So as I'm going to discuss, what happens as a result of this increased warming is more wildly fluctuating weather patterns, including increased snowfall. So that's why scientists around the year 2014 started using the terms climate change versus global warming. So what we're seeing with these change in weather patterns is just globally big changes that have huge implications for the individuals living there and the organisms living there. So let's start with talking about those changing rain and snow patterns. So because we could predict with some regularity what the climate was going to look like, because we knew what to expect based on previous data, all right, we could say, all right, this is going to be a bad year for winter or whatever. But because of these exponentially different seasons that we're getting because of the increased temperatures, we're getting wildly fluctuating rain and snow patterns that we just weren't expecting. So what's happening basically is stronger storms, right? And we've seen that in the past years here in Florida with these Category 5 hurricanes. It passes over warm waters and becomes a Category 5 hurricane in a day. That is unheard of, right? And I have lived in Florida all of my life. We'll see, in the winter times, not here in Florida, but in other parts of the country where they'll get, again, 10 feet of snow, where that was unheard of previously. And it's because of there are, these global air circulation patterns, as you guys know now, and as they change temperature, they're going to start to shift because it's temperature that's guiding that, right? And so they'll become more intense in areas that were previously not intense. It will become stronger, and we're not going to see any change or relief from that anytime soon. Okay, so in those areas that, like here in the eastern part of the United States, that are going to expect more in terms of rain, we're going to get increased rain. In areas where there would have more snow, they might get increased snow. But in areas where they're going to have more drought, like we know in California and Arizona and Mexico, there'll be increased drought, right? And that in turn will lead to increased chance of wildfires. All right. In the city area, we're going to see higher temperatures, which lead to heat waves. And we're going to talk about heat waves in particular in just a minute, but that can be deadly for the most vulnerable residents. In the oceans, that will lead to damaged corals as well as rising sea level, but as a result of being warmer oceans. We'll also see changes in plant life cycles and animal migration and life cycles, right? So we are seeing that. I'm going to talk about one particular insect we're seeing as a result of climate change, a change in their life cycle, but also just because the topic interests me, beer production. So this actually has been going on for quite a while. The areas where you can grow hops are now shifting to the north because it needs a little bit cooler weather, and it's because it's so warm in certain spots they can't produce hops there anymore. In areas like Russia, which we talked about this when we talked about the Russian Federation, they are seeing a thaw of the permafrost. And initially, Russia thought that was going to be a really good thing, but what it ended up was causing sinkholes, right? Because it released methane gas, and the soil collapsed inward, and it actually has been pretty horrible. They realized, oh, that was not a good idea. And then finally, in areas where we have snow and ice, like thinking about when we talked about the Middle East, certain areas like the Anatolian Plateau in Turkey or the Atlas Mountains, they would get rain and they would get snow in the winters. And that runoff is crucial for the survival of the people living in those areas. But if they don't have that, then the people who live in the area where that runoff is coming, they're not going to have water. So this is a huge impact on an entire global system. And we're going to talk about a lot of these in more detail. All right, so let's talk about sea level rise. As I said before, the major cause that we're seeing so far is the thermal expansion of water. As water is getting hotter, it's expanding. But also the melting of sea ice. So this is our Antarctic ice sheet. And those areas where it's like a purpley pink color is where the ice is thinning. Okay, so we actually have seen parts of the Antarctic already breaking away, which will increase sea levels. So this is from NASA, and they've been monitoring the mass of the sea ice in Antarctica. And as you can see, it has actually decreased since even the beginning of the 21st century. So it's at its lowest it's been in many years. Same thing going on in Greenland, pretty well tracking that data. All right, so let's talk about extreme weather events. So again, we've experienced those here in Florida. And as the climate changes, we know that it is likely that the frequency and intensity of extreme weather events will change. So we'll see expansion of those. Although some of the preliminary evidence is suggesting that although there may be more intense hurricanes, there actually might be less, which would be great. Although not good if they hit us when they're intense. But in any case, not just hurricanes, of course, but also expanded heat waves and changes to things like El Nino, right, which will bring global changes in weather patterns. So as I said, it was likely to increase heat waves. So what is a heat wave? Well, this is defined as a minimum of 5 consecutive days where the high temperature is at least 5 degrees Celsius above the average. So obviously this is also most often going to happen in places that are already prone to heat, right? So in the city space, we're going to see this happen a lot. So what we see in urban areas like, big developed cities like Chicago or New York is because it's such a concrete jungle, right? That the concrete is an excellent absorber of heat, right? And so what that does is trap the heat in and doesn't allow it to escape. Like in green areas, it will cool the temperature down, whereas in the cityscape, it doesn't, right? It's a concrete jungle absorbing that heat. So there'll be even higher chance of increased heat in those places. And then just overall high temperatures in the globe, right? So places like Australia, if you've seen that in the news, there's a lot of scientific evidence to suggest that the wildfires were as a result of climate change. So as recently as last winter for us, so summer for them. So remember, they're in the southern hemisphere. So in December 2019, which was our winter, their summer, they saw an average temperature of 107 degrees Fahrenheit, right? Which passed the previous record that had been set in 2013. Realizing again that those wildfires are probably due to climate change, right? And so this is one of the things they were talking about, which is that because now it's so unpredictable, because weather is just fluctuating wildly in a way that we're not sure how that's going to go. We had, a combination of extremely hot temperatures with wind conditions that they weren't planning for. So where the most intense heat for Australia was, again, in those areas where unfortunately people are living. So along the northwest coast of Australia. And then, of course, in the interior, which if you know anything about the interior of Australia, it's basically the outback. So that wildfire spread then brought on by basically severe drought in the country, or in the country/continent as well. So behind the heat wave, this increased temperatures of the ocean, right? Also exacerbating the heat waves, especially in Australia, being a continent that is surrounded completely by water, right? So that in turn, of course, causing those heat waves. So what we're looking at here is the probability of occurrence of our heat waves, right? So there's going to be an increase in terms of the average high temperatures. So where places like, you might have seen in Australia where the average summer temperatures might have been in the 90s in degrees Fahrenheit, now may well see the new normal of being average temperatures being in the hundreds, right? And then as you're going to see too, like just not even just more hot weather, but more record hot weather as well. So this will also lead to precipitation change. So thinking about, again, just extreme weather, Hurricane Harvey, right? So areas like the southeast, which are prone to heavy rainfall anyway, are likely to see a great increase in precipitation, right? So as you can see, like in the Midwest, as well as in the New England area, we may see an increase in precipitation of higher than 15% increase, which is a lot. I know that doesn't seem like a lot, but it is actually quite a bit. And perhaps some increased dryness here in Florida, or hopefully no change. But what that means too is, remember, this is basically what we call a breadbasket. So thinking about, again, when we talked about the United States and Canada, that's where most of our agricultural production is happening. So if we have increased rain, that might mean that some crops won't survive. It seems like a great thing to have a lot more rain, except you'll also get increased flooding. So if you've been paying attention to the weather at all, the Midwest has experienced quite a bit of flooding. And remember, that's also generally the area where we have the Mississippi River. So that levee and dike system that we put in place to basically try to control the flow of the river, probably not going to work so well, because now we've added a much higher volume of water to the river. So what that means then is we're probably also going to see increased flooding events in the area of the Mississippi River. And then again, in areas that are already prone to drought here in the United States, like again, New Mexico, Arizona, and then into Mexico, we'll probably see also increased drought. So those areas may become unlivable, right? Because we may not have enough water to supply them. So as I said, one thing that is good/bad is that does seem like we might see a decrease actually in the frequency of hurricanes, because what's happening is it's a little bit complicated, but we have micro changes in the wind. So what we might see is, because you need a little bit of stability in the upper parts of the atmosphere in order for the hurricane to form, is that there might be so much change, so much variation, so with the winds moving so much that it has a harder time forming. But what we do see is that obviously the fuel for hurricanes will be increased. So we'll probably have an increase in category 4 and 5 hurricanes, with those wind speeds being able to increase pretty well exponentially, right? Obviously, sea level rise is going to also increase the impacts that we see from hurricanes, because we'll get that coastal flooding, right? So that the area of damage is going to be extensive. And one thing that is not as readily apparent, people don't always think about it, but we do have inland inundation, where basically water is coming up from underneath. So we will see that as well as a result of hurricanes and storm surge. And as I said before, we get increased precipitation. We'll also see heavier rainfall, just like we saw with Hurricane Harvey. Also seeing those hurricanes shifting towards the poles, right? Because we'll see an expanding area of the tropics due to higher global temperatures. So that means that those patterns of tropical storms are going to shift towards the north. But right now, obviously, a lot of this is a prediction, so we're not sure. And again, so this is talking about that storm surge, and that basically the high tide, if those two things coincide, not going to be good for anybody living near the coast. So taking a look. So here's our high tide mark for 2010. And then there's our storm surge. So a house located near the water in 2010 might have seen a little bit of flooding. But as we get to the 2015, right, or excuse me, 2050 projected high tide, now it's getting even closer, right, to that house. And now our storm surge is basically in the house, right? It's covered that beach house. And then we get like 2100, right? Well, the high tide, the house is underwater. So you will not be able to build in that area. You'll have to build further back. And the storm surge will actually now reach the cityscape that's further away from the water. So what that means is places like Florida, you're probably going to have to start building much further inland, right? Obviously, there's a lot of factors that are going to go into that, like your ability to respond, so the type of housing that we'll see in that area, things like the tides, any natural or artificial barriers, and the contours of the land. So this is a general pattern. Doesn't necessarily mean that your coastal house is going underwater, but it is something that you might want to take into consideration if you're talking about buying property here in South Florida. All right, so things like ocean acidification. All right, so what's going on is, I think I mentioned this before, as we take that CO2 into the ocean, which increases the temperature, it decreases the pH, so it makes it more acidic. So just very briefly, talking about the pH scale, on one end is very acid, right? And so that's going to be from 1 to 6. 7 is considered neutral, and then 8 to 14 is basic or alkaline. So you'll see things like on the acid end is going to be like vinegar, and then on the basic end or the alkaline end is going to be like baking soda. All right, so just kind of put that in terms that you might understand. So what we're seeing is, and this is a general pattern, when temperature increases, pH decreases, right? And also that absorption of carbon dioxide also causes that decrease in pH. So our organisms that live in the water, so the ones that are shell building or having a skeleton, rely on alkaline conditions in order to build their shells or their skeletons, right? They need basically calcium to do that. So if you've been out to the beach or anywhere like in Miami and you've seen that limestone is made up of the shells and the bones of dead sea creatures, right? And it's very basic, it's alkaline. And that's that raw material that allows the organisms to build their shells and to build their skeletons, and also what we need for the coral reef, right? So if the acid conditions become worse, then they won't be able to do that. And we're already seeing that happen a little bit with our coral reefs. So coral reefs, obviously beyond being a tourist attraction, thinking about like the Great Barrier Reef, which parts of it have died, right? Also providing coastal protection. So we do have reefs here in Florida, and they protect the coast from major storm impacts. If they are no longer there, they're not going to do that. They also, of course, provide food for many of the fish in the ocean. So this was especially the case in the northern part of the Great Barrier Reef, where we've seen declines in the coral. So obviously we'll have coral bleaching, and then other things affecting the corals too. It's not just the ocean acidification and warming, but also things like invasive species. So we'll talk about that more in just a second, but quite a bit of the coral, the Great Barrier Reef has been degraded, right? So just to explain that, right? So as I said before, a lot of the CO2 is being absorbed into the atmosphere, or into the ocean. So it gets absorbed in the ocean surface, and eventually it starts to sink down towards the bottom of the water, right? So I wanted to show you this chart, which is showing the pH of the ocean. So, and the change relative to the pre-industrial pH, right? And then the hydrogen plus, so that's again affecting our pH relative to the pre-industrial. All right, so the pre-industrial pH of the ocean was around an 8, again, so that is alkaline. All right, so remember 7 is neutral. So in the recent past, so the 1990s, it dropped a little bit, not a ton, right? So increasing the hydrogen ions that are in the water, okay, by about 20%. At the present levels, we are still declining, so still around at 8, but still dropping, right? And so the ions increase in the water to now about 30%, right? Then we're predicting for 2050 to be below 8, which now is more neutral, but that means that there'll be 70% more hydrogen ions in the water, right? And then by 2100, 126.5% more hydrogen ions in the water relative to the pre-industrial period. All right, so that is a huge change. And knowing that ocean acidification is different than coral bleaching. So here is a little graphic showing ocean acidification. So when we talk about coral bleaching, thinking about corals, they are an animal, they're an organism, in which there are these many different polyps, which are what we call the thing that lives on coral. And they have a single-celled algae that lives within their tissues. So when we have coral bleaching, it loses their color, right? It expels that algae, it dies, okay? Bleaching, obviously very severe in years where there's a higher ocean temperature, so that's what we're seeing, right? Ocean acidification then is what we're looking at in this image. So a lot of our human activities releasing carbon dioxide into the atmosphere, and the oceans are absorbing that carbon dioxide, as you're seeing. So remember what I told you, it's starting to dissolve and sink down into the water, right? It forms this mild acid in the water, but basically what happens then is it makes the water acidic. And then that overall has a big effect on our ocean ecosystems. So as they become more acidic, so you can see that there is carbonic acid that is in the water, right? And remember what I was telling you about those hydrogen ions, there's an increase in hydrogen ions. So as it becomes more acidic, there's more of them in the water, which is going to eventually lead to deformed shells because it's going to affect the way that they get that calcium, in this case, calcium carbonate, all right? So with the oceans becoming more acidic, there's less calcium carbonate available in the water, and then what that happens, the calcium carbonate in marine organisms dissolves, all right? So those are those two different events. I want to make sure that you understood that. So there we go. Coral bleaching, water's too warm, and they expel that algae that is inside of them. Again, the coral reefs in particular, big trouble due to both the bleaching from the warmer temperatures and then also coral bleaching as a result of human activities like touching them, so like from diving, but mainly from sunscreens. So most of us in the past, maybe hopefully you've switched now, but use the chemical-based sunscreen, right? So that chemical that is in the sunscreens is highly toxic to coral and other animals too in the ocean. But obviously it's going through our water. So like if you're in the shower and washing it off and then it gets dumped into the ocean, so now that's getting just a little bit of that sunscreen, but obviously mostly coming from when you put it on and then go into the water, right? So also in like cosmetics, ladies, if you wear like a cosmetic that has a sunscreen in it, basically just watching in terms of like washing that off. But other things that we can do is just basically use mineral-based sunscreens. Just don't do that, right? Don't wear the chemical-based sunscreens. So yeah, but that's basically what's going on with our corals. Okay, so that is the kind of explanation of the physical changes that we're seeing as a result of climate change. So let's talk about the human effects and the impacts of climate change. So what are we going to see in terms of like our land space and on human health? All right, so what we're probably going to see, unfortunately, is an increase in the range of some of our pests and then, of course, disease-carrying insects, right? So things like mosquitoes are going to increase their range. Things like rodents might increase their range because now as the climate gets warmer in a lot of different places where they might not have been previously because it was too cold for them. Now they'll shift to further have a bigger range, right? So things like mosquitoes, as it says in the slide, spreading into warmer climates, right, which gives them also a faster reproductive cycle. And unfortunately, when we do have that increased flooding, we're also having the increase of standing water. So this is also, I think it was last time we had a major hurricane, they were telling people to go outside and, make sure you turn over any buckets or anything that would have standing water in it, because you didn't want to create a pool where mosquitoes could lay eggs and then have more mosquitoes, right? This is one of the things we have to worry about. And heat-related illness, which we'll get into specifics of heat-related illness in more detail in just a minute. So what are the impacts of climate change on human health? And they are numerous, unfortunately. So when we talk about severe weather, obviously leading to things like injuries or fatalities, but also mental health impacts. We don't actually talk about that a lot when we talk about extreme weather events. But there's been a lot of scientific studies, surveys that have been done after a major storm event has happened, like this one was, I was thinking in particular about Hurricane Harvey, and many people reported symptoms that would be similar to post-traumatic stress syndrome, right? So that's a possibility as we see these major storm events. As air pollution might increase, you'll also see the increased chance of asthma or cardiovascular disease. We saw that in Australia, right? There was an increase in respiratory effects as a result of these wildfires. And same thing happening in California and, parts of the West when they were having the wildfires. As a result of air pollution and that particulate matter from fires, increased cardiovascular and asthma. Increases in our vectors, changes in our vectors, right? So those vectors are like the rodents that I mentioned or the mosquitoes. We're going to see sicknesses that were typically only found in tropical areas starting to expand where they are found, right? Increasing allergens. I'm not sure if I'm the only one who has experienced this impact, but in the past probably 2 months, I've had really horrible allergies, and I wake up every single morning with an alert from WeatherBug, which is my weather app, that there is a high pollen, like actually even today, right? It's high pollen concentrations. And so as we see a increasingly fluctuating weather pattern, so like for example, here in Florida, we're actually a little bit drier than we normally are this time of the year, which is what's increasing those allergens. We will see an increase in respiratory allergens and as a result, asthma. We will also see impacts to water quality. So remember when we talked about water, when we talked about the Middle East and Sub-Saharan Africa and India, right? And so waterborne illnesses, one of the top 3 killers of people worldwide. It's still one of the top 3 killers of people worldwide. And because of climate change, we'll probably see an increase in water quality issues. Because for one thing, thinking about that increase of nitrogen, remember we talked about the nitrogen cycle, nitrogen going into the water is what causes those algae blooms. So again, here in Florida, if you haven't paid any attention to that, they got the blue-green algae in Jupiter, or we got red tide over in the other coast of Florida. And what causes that is the same cause with just different organism, is the nitrogen. So it's fertilizer, right? And it causes those harmful algal blooms because what happens is they release a hepatotoxin that is going to attack your liver. Or other impacts from water quality, things like cholera. Don't think about cholera now because we treat our water. We don't have that problem. We have medication for cholera, but it was a huge killer in our past. And in other parts of the world, this is still a reality. So cholera outbreaks even being reported in the past, 10 years. So cholera hasn't gone away. And if you're not familiar with cholera, it's a diarrheal illness that's from a bacteria in the water. So if we don't have quality water, going to spread waterborne illness. Then environmental degradation, we don't think about that as something that's going to impact human health, except if you recall, again, when we talked about the Middle East and North Africa, that was part of something that fuels that Syrian refugee crisis, right? People leave Syria because of a drought, right? It was a climate change related drought, and they are forced into the major cities because they're looking for water. And what's going to happen is that increases the possibility of conflict, right, as it says on the slide. And then again, finally, in extreme heat, we have those heat-related illnesses and death, as well as cardiac failure. So we're going to talk about that in just a minute. Okay, so as I said before, we're going to talk about one particular insect that is kind of like the harbinger of climate change, and that's ticks. All right, so ticks, a vector-borne illness, right, because they're going to spread Lyme disease. So there is already evidence that ticks are going to spread to higher latitudes and altitudes in both Canada and Sweden. So the EPA is actually tracking Lyme disease across the United States as one of the first diseases, the first epidemics of climate change, right? So it's an official barometer of climate change. So let's take a look at that. Okay, so this is an area of Canada, right? And it's showing the increase of risk for Lyme disease, right? So as you can see, some areas now have a much higher risk for Lyme disease. And obviously this is Canada, so we're up near Maine and New York and Vermont. Obviously those states here in the United States will also be very prone to Lyme disease, right? But this is from Canada. So all those areas that are in yellow we have a moderate risk, and then in the orange is a higher risk. And this is shifted to the north, right, where it was previously not seeing a risk to Lyme disease. So this is also an impact to animals. So we think about it obviously in terms of human health, and Lyme disease is a serious illness for which we have no treatments. But that also means things like moose, seriously impacted by ticks. So this is, and I can't show you this because it doesn't work, but I'll put the link on Canvas. This is a moose that had so many ticks. It had no tick-free spots on the sensitive areas of the poor moose, right? So we'll actually call these moose ghost moose, right? And they will go, and you'll get some evidence of this by them rubbing on the trees because they were trying to scratch themselves because they're so itchy. It's just so loaded with ticks that the poor thing is just miserable, right? And so as I said, there's not one tick-free spot in the sensitive areas of the poor moose. All right, here's some stuff for the United States. Okay, so predicted Lyme disease risk in the United States. Obviously, it's going to differ. This is just predictions. But as I said before, in those areas where, here's kind of where we were before, it's in Canada, so increased risk because it's starting to shift to the north. High incident in New England area, as it always has been, but now we start to have higher risk in other parts of the United States where previously we really had no risk of Lyme disease. And so actually one of the concerns that's come about from the Lyme disease risk, that change in Lyme disease risk, is doctors are not, in certain areas where they didn't have Lyme disease before, the doctors were not familiar with diagnosing that illness, so they might miss the signs of Lyme disease before they start to realize, oh, that's what this could be, because they weren't expecting there to be Lyme disease in that part of the country, right? And so the person might go untreated for a long time without the doctor recognizing that's what it is, right? So one other thing that's been happening in terms of like the scientific community and understanding what's going on, they realize that because of this increase in temperature, that increases the chance of the tick's survival, right? And that also obviously makes better conditions for the animals that they live on, like deer. So in terms of like looking at this increase in temperature, that means that we might see an increase overall of 20% increase in Lyme disease, right? So that is something that obviously physicians need to be aware of, okay? So other vector-borne illnesses, including things like our ever-present mosquitoes during you guys are too young probably, but in 1998 to 1999, that was the first ever recorded West Nile virus outbreak here in the United States. Okay. Mosquitoes are obviously one of the ones that we are probably most familiar with in terms of spreading sickness, right? So it's other things like encephalitis, malaria, and things like that, right? So these warmer temperatures that we are experiencing, as it says in the slide, allowing the mosquitoes to increase their range, having more production, like reproduction, and of our parasites that are in the mosquitoes as well. So like it says, malaria is a parasite. And again, that increased flooding, giving more standing water for mosquitoes to reproduce. And there's also some evidence, which is unfortunate for us, that mosquitoes are becoming more tolerant to salty water. So as we see sea level rise also increasing the standing water, mosquitoes are adapting to that, right? So not a good thing. So that's something that we have to be aware of when we talk about climate change, is how is that going to impact human health? So what are some of the vector-borne illnesses, including West Nile, dengue fever, right? That is the breakdown fever, right? And that rose 70% from 2012 to compared to 2011, with the majority of cases, as you might imagine, in Florida, where we have obviously already a lot of rainfall and mosquitoes. Chikungunya and Rift Valley fever, which are typical to tropical Africa and Asia, starting to see cases in Europe as the spread of mosquitoes happens, and expected to enter the United States as well. And again, these are sicknesses to which we're not used to, we're not too familiar with here in the United States. So doctors are not necessarily looking for the signs of those sicknesses, which means that, especially for physicians, forewarned is forearmed, right? They need to be preparing for these sicknesses, and yet in some cases that's not happening because they're not recognizing that this could be a possibility. And as it says, so disease cases from our vector-borne illness, so things like mosquitoes, ticks, and fleas, tripled in 13 years. So from 2004 to 2016, we went from disease cases at 27,388 to, in 2016, 96,075 disease cases. So this is directly from the CDC. It's not from some random website. It's from the Centers for Disease Control. And so recognizing that climate change actually directly impacts, public health. So when we talk about public health, that's the health, obviously, of the public as a whole. So not just on the local level or an individual level, but everybody. Usually when we talk about public health, we are talking about the entire globe. And we actually saw that when we talk about coronavirus. Coronavirus obviously is a global pandemic. So we have to talk about the health impacts to everyone on the globe. If you're talking about just one isolated community, that's actually not an effective means of stopping the sickness. All right, and so that's actually some of the things that we have to do with when we talk about vector-borne illness. I'll talk about it as a global community, because the chance of that shifting to other parts of the world, not just going to impact tropical areas, which unfortunately we ignored that for a long period of time. So these are the estimated deaths as a result of climate change. Obviously, this was in the year 2000, so some change. Where do we see? Obviously, the highest impact is going to be places we might have already expected: Sub-Saharan Africa, Northern Africa, and the Middle East, South Asia, places where there's a high population density and not enough income in order to respond to those illnesses, right? And so one of the other things that we see as a part of climate change is unequal impact to people around the world. And we've discussed that before. But this is where, if you've seen things like where environmental justice, clearly some places will not only have much higher incidence of mortality related to climate change, but also just lacking the ability to respond to that. And one more. right? So microplastics. So this is was a kind of a big deal when that ended up. Um, it's been tons of different studies that we found water, microplastics in our water, in our beer, in our salt, and in our feces, right? So this was a small study that had just found that, we have been digesting it and it's going through our digestive system. So just that sheer volume of plastic that is in our everyday lives, all of those things shed plastic. Okay, and so where do those little microparticles of plastic end up? They end up in the water and they end up in the air. So we're breathing it in and then we are also consuming it. So obviously this was a small study. Most of these are minor. We really don't know what the impact to human health is going to be. We know it's probably not going to be good, but knowing that, yeah, this is a concern. Probably really don't want to be consuming plastics on the reg. All right, so how might climate impact agriculture? So in some plants might see a benefit actually from the increase in CO2, right? Because remember, plants absorb that, so they like it. So it actually might help some plants. We will also see some shift in crop range, which can be good and can be bad. So that was one thing that we discussed. Again, we talked about the Russian Federation, that they were happy a little bit with climate change because now that allowed them to actually plant things. Because the permafrost was thawing, now they could have more agriculture in areas that they previously weren't able to have it. We'll also see increase in irrigation because now precipitation is changing. So we'll need to draw off already existing water sources in order to water our plants. Most likely not going to be a good thing. As we saw, again, when we talked about Russian Federation, the Aral Sea, if you remember, they took all the water from that inland sea for their cotton growing and ended up basically killing off that area, right? There was no more fishing and still really didn't have enough water for the cotton. Obviously, as we were just talking about, vector-borne illness, this is not just impacting humans, it does impact livestock, and we'll also see blights that might affect crops as well. So overall, the impact to agriculture is not going to be good, although there may be some benefits for some plants. So as it says in the slide, what that means, our warming climate means that the range for crops will change. Like in cooler regions, like Russian Federation and parts of Canada and parts of Europe, parts of the United States, this might actually benefit them because they have a longer growing season. So we have that here, right? We won't really have a time of the year where in Florida you can't grow plants. It's pretty hot in the summer, so it makes it a little hard, but for the most part, we can grow plants all year round, and we'll see that in other parts of the world as well. So this is one looking at just agriculture in the European Union. So in Scandinavia, we'll have decreased summer rainfall, increased winter storms and floods, which increases the length of their growing season and gives them increased yields. So it'll also increase their suitable farmland, unfortunately, also increasing the pests and the disease risks in that area. In areas like the UK, increased flood risk, hotter, drier summers, and increased sea levels might make this area actually less desirable. So in southern Europe, we'll also see, because it's already drought prone, a decrease in water and an increase of drought risk, which means we also have increase of heat waves and increase of possibility for wildfires, which also means we might have an increase for soil erosion and a decrease in our growing season and crop yields, which means we'll have decrease in optimal crop areas, which means, remember, we have a Mediterranean climate. What's going to grow? Yep, grapes. So our wine production areas may decrease. And here's in Russia. This is from 2011 to 2015. So looking at the ability to produce more wheat, right? They have actually a higher chance of producing more wheat. So in some areas that will be benefited from climate change because the growing areas will be increased. So as I said before, beer, right? I swear I'm not an alcoholic. I just studied this for my dissertation. Okay, so barley is one of the necessary components for beer, but it does require certain conditions to grow. So it mostly likes, if you remember that marine coastal environment, so it's going to be cool and there's a lot of moisture. So like it says in the slide, we need the Goldilocks conditions, right? So a lot of the areas where we see barley production in the United States is in Washington and Oregon. So unfortunately, we've also seen in those areas some change in the climate, right? So increased drought, increased heat waves. This is not good for beer, right? So we will have a decrease in beer production as a result of climate change. There's been some global look at this as well. One of the main areas where we have production for barley and hops, which is in Belgium, also experiencing the exact same thing, right? So we may see a global decrease in beer production and a global increase in the cost of beer. And I think tea is the #1 consumed beverage worldwide, but the second or third is beer. I don't remember off the top of my head, but it's up there. So I just bring this up because, you know, my thing. But so climate change obviously impacts beer. So warming reduces the snowpack that we would normally have for irrigation. So we may again have that increase in irrigation is needed. Higher dependency on groundwater, which also has a lot of minerals in it. So you remember when we talked about Australia and we had that artesian aquifer. So it's becoming increasingly salty as people have been drawing more and more on the aquifer. That's what they're talking about there, that groundwater has a lot of minerals in it. And so it will basically change the way that beer tastes and also the fermentation process. And as I said before, we'll probably see a global decrease in the amount of beer being produced, so a global increase in the cost of beer. Some other impacts to beer, as I said before, not just barley, but hops. So in our Pacific Northwest areas where most of those grow, hops are also really picky in the areas where it will grow. They're not tolerant of temperature or moisture swings, so most likely we'll see a decrease in the production of hops. What about Africa, which is already in a not great situation for agricultural production? If you recall, when we talked about the soils of Africa, they're relatively poor for agricultural production. And so this is focusing specifically on cereal production, which is cereal grains are one of their staple crops. So our current predictions for atmospheric carbon dioxide concentrations. So this is actually a pretty high concentration. I hope we don't get up that high, but as it says, probably that combination of increased temperatures and decreased rainfall will be devastating for places like sub-Saharan Africa. So here's that Sahel zone, if you recall. That's most likely going to become just a larger part of the Sahara. This area is not going to have too much change because it's already the Sahara Desert, right? We'll see increased change to the areas that currently have some moisture will probably also become pretty dry. So as you move further to the south and in the center, we actually might see more people move towards the center. Unfortunately, if you recall, again, this is the Congo area. So what might happen is because people are forced into the center, we'll see more competition over limited resources and probably an increase in people who are catching those tropical illnesses because they're moving into the areas where those mosquitoes are. So this is probably going to have a devastating impact on sub-Saharan Africa. Other changes globally, right? So United States actually might have increased agricultural productivity in the northern part of the country because warm weather is shifting to the north, but in the south we'll probably have a decrease in agricultural productivity. Pretty much staying roughly the same for California, which is good because a lot of our crops are grown in there. If you can see though, most of the world is not going to be benefited by climate change. So Mexico, Central America, South America, most of Africa, the Middle East, South Asia, Southeast Asia, Australia, all of those areas heavily impacted by climate change where we see a decrease in agricultural productivity. And if you're not able to read this, Our red, yellow, orange colors are a decrease in agricultural productivity, and the greens are the increase in agricultural production. And as it says here on the slide, so that key culprit in climate change might help agriculture by enhancing the photosynthesis of a lot of different plants. However, we don't know what exactly is going to happen. So I think overall the prediction is going to be a decrease in agricultural production, but we still just don't know, right? That's one of the problems with climate change, is that there's so much going on that we're just really not sure about. We're not really sure about the impacts. All right, what about conflict? So climate change also leading to conflicts between peoples, right? I think we discussed that a lot, where access to resources means that people are going to be fighting over those resources, right? So as it says, environmental refugees, which are fleeing extreme weathers, things like drought or famine or sea level rise, and will increase them having to move, which means that we either have to take them or we say you're not coming and then watch them die. So that's going to be that will be a conflict we'll have to deal with, right? So let's look at these in more detail. So one of the things where we might see, it's a little bit of conflict. It's not, a massive conflict, but there's conflict, is the opening of the Northwest Passage, which is a passage in the Arctic Ocean. So previously this was permanently covered with sea ice, but now has opened because of climate change. So everybody around that is wanting to get in there and claim that area as their own, right? So it's Canada and the United States. Again, not something major in terms of conflict, but it is a conflict, right? So the United States claims it's international waters. Canada says it's their internal waters. So in 1998, both countries had agreed that the United States would first ask before sending in an icebreaker. However, as the ice melts, as in traffic might increase, an agreement between the neighbors might not end up being enough, right? So as you can see on the slide, so in 1988, which is when they made this agreement, 11 ships traveled in the passage. By 2016, 47 ships did, according to the data from the U.S. or the Canadian Coast Guard. So again, it's not a major conflict, but it is a conflict related to climate change. And we've seen others, right? Your MENA map activity was dealing with conflict, right? Access to water. We'll see that, in terms of like agricultural production. There's a ton of conflicts that are likely to result as a result of climate impacts. All right, so there's that route through the Northwest Passage. So as you might imagine, in the past, this was pretty well covered in ice, but now is more open. Conflicts over water, which is probably one of the #1 conflicts we're going to see, because it's necessary for life. People are going to demand water, and we'll see how important this is in terms of the world, right? So as it says in the slide, as precipitation changes, as glaciers start to melt, as salt water intrudes into the groundwater, which now makes that groundwater undrinkable, we will see increased competition for fresh water. And we know that we have seen that access to water is a major source of conflict. And then in environmental refugees. So again, we saw that when we talked about Syria. Refugees often forced to flee their homes due to human violence, like war, terrorism, or persecution, which might result from climate change as well. There might be a battle because of climate change. And when people leave an area because it has become undesirable, it is called the what of migration. Yes, that's right, the push of migration, right? So that the push is something that pushes people out of an area. The pull of migration is something that draws people to an area. So in Bangladesh, we are seeing some of that, right? So climate change in Bangladesh has started what might end up becoming the largest mass migration in human history. So we're seeing riverbank erosion here in Bangladesh, which ends up displacing a ton of people. At the 3-foot level and sea level rise, about 20% of the entire country will be submerged, which means that more than 3 million, 30 million, people would be impacted. So where are they going to go? That's the major concern as well. Not just that they're losing their homes and everything else, but they have to go somewhere. Where are they going to go? We don't know. All right, so here's some maps of that, right? So in the dark green is our very heavily populated areas. And do you guys remember what this estuary area is called? Yep, it's the Sunderbans, right? And so there's a ton of people living here. It's very productive estuary. So if we had 1 meter, so this is about 3 feet, of sea level rise, you can see a huge chunk of the Sunderbans are submerged. If we had 1.5 meters of sea level rise, now we're moving even more into those very heavily populated areas of Bangladesh. So again, where are they going to go? We don't know. It will likely cause conflict because now they are forced to go into, either if they go into India, which is already heavily populated. Remember, India is a Hindu country. Bangladesh is a Muslim country, right? So, sorry, I mixed the West Pakistan, East Pakistan, and Muslim, all that transposed in my head. But in any case, they are a Muslim country. So they go into India, that is a Hindu country. So there might be conflict there. Or if they go to Pakistan, remember, they fought to be separate from Pakistan. So how is that going to play out? Again, we really just don't know. We don't know what the story of this is going to be. And we talked about this before. A lot of the water contaminated with arsenic, right? So we probably see an increase of that because if you recall, when we talked about that with South Asia, it's some of that has to do with the tapping of the water. What happens is it converts the arsenic that is naturally occurring into a form that is going to poison people, right? So if we have a lot of increased flooding, it will most likely have more of the water be contaminated with arsenic. And here's another map showing you, again, that's the percentage of the wells in Bangladesh contaminated with arsenic, right? All right, heat-related illness. So this is actually one of the deadliest weather hazards related to climate change, right? So what could happen as a result of exposure to high heat? If you are not familiar with this, right? So you might get things like heat cramps, heat exhaustion, or the worst, which is heat stroke. And yes, this can kill you. Who is most at risk? Obviously, people who are low income because they probably don't have the means to keep their homes cool. The very young children, and then the elderly. So this has happened. Heat-related illness already occurring, right? So this was in 1995 in Chicago. There were, if you can see, so let's look at the temperature. So this is July in 1995 in Chicago. And you can see our temperatures were approaching 105 degrees. And remember, we're in that cityscape, which is already just super hot. And as you can see, there were 739 heat-related deaths. So obviously these were actually mostly poor elderly people who didn't have air conditioning and couldn't sleep with their windows open because they had a fear of crime. So again, you might not know much about Chicago, but it being in an area where there's a lot of crime, unfortunately, it's a major city area. It's also in the Midwest where it's mostly cool, so a lot of homes don't have air conditioning. So either, they couldn't afford to get air conditioning, like a window unit like we might have down here, and then, not being able to sleep outside because they're afraid they're going to get murdered. Basically, people died in their house because it turned into an oven. So what might that look like on different areas in the United States? So that increased heat. So just kind of across the board, you're especially going to see it in, obviously the South where the temperature is going to be higher, right? But just across the board, higher energy demand, increase in heat-related mortality, increase in coastal damage, increased demand for water. It's not going to be a pretty picture. And I already mentioned Australia. But in 2000, it was 2018 that I made this, but I just talked about 2019. Broke records. It actually reached 120 degrees Fahrenheit in some areas. Increased fire and drought across the board throughout the continent, killing off many different animals. So as you can see in the image, I mean, animals just dropped dead from heat because it was so hot. The roads were melting. It was so hot. I know, like, one thing I remember from the reports that were coming out of this, like the mailboxes melted. It was so hot, right? So the mail couldn't be delivered because the mailbox melted. And because there was such a high power draw, they actually cut off the power because it was so high that they were just like would melt down. So they ended up having to cut off the power, and then that, of course, turned off the AC. All right, so what is the climate impact on Florida? So I just want to end this by talking about the specific impacts on Florida, since that's where we are. For the United States, unfortunately, Florida is on the forefront of climate change because of our coastal low-lying position. All right, so economics, health, all of that at risk from climate change. As you can see in the map, if the sea level were to rise about 6 meters, which is about 20 feet, all the areas in red would be underwater. Okay, so I think I've mentioned this inland inundation, or that saltwater intrusion. So I wanted to show you an image of that. So in a typical city coastline, which doesn't have limestone, and we've got a seawall, the salt water is not able to penetrate into the rock because it's not porous, unlike our rock, right? So it stops the salt water from going under. But in Florida, because we have a limestone foundation, which, as I've discussed many times, is very porous, it allows the salt water to seep under the seawall and then intrude eventually into our aquifer and into our land space. So increased salt, going to kill plants, damage to, I'm an archaeologist, so I think about that, damage to anything that's buried in the ground, but also obviously contaminating our water supply with salt. So increasing these, with the increase of these major hurricanes, so like it says, in 2017, Hurricane Irma made landfall as a Category 4 hurricane. Irma caused $50 billion in damage and destroyed 25% of the Keys. Without sea level rise, the storm surge would have been lower, right? So that's, again, that impact of storm surge. So we're seeing that there, right? So in the last 31 years, we had 6 inches of sea level rise, and in the next 15 years, we're predicted another 6 inches of sea level rise. And again, so that backing up into our pipes, into our drainage systems. So normal times when we have storm water runoff, it's not too bad. It will keep the storm water out, right? But unfortunately, the ocean pressure, because it's so increased, it will back up into the pipes, and then salt water again intruding into our drinking water, into our land space. So the roads might flood as a result of being low-lying, which if you've lived in areas where that's the case, it's horrible, right? Things like Miami is already happening. You know, you're driving down the road and you're basically driving through water if you're able to drive at all, right? So as it says, making it difficult or impossible to do. The drinking water might mix with salt water, which will ruin the well. You won't be able to use that well anymore. A lot of areas in Florida also are septic, which might be impact from high seas, or the sewage systems. As you can see, if they become damaged, we're in trouble, right? That's going to be a human health hazard, because that's one of those things that causes cholera. And of course, as I said, I'm an archaeologist. Those are the things I worry about. If we have that increase of sea level rise, you can see it's going to extend that far inward, and we're going to be impacting just a ton of archaeological sites. So if we had that much sea level rise, almost 100,000 archaeological sites would be impacted. And that, again, we are also at the forefront of health concerns as a result of climate change. So allergies, asthma, heat-related illnesses, vector-borne disease, like with the king tides, if you guys have seen that in the news, right? That even more increase of standing water. And so this is mosquito abundance, right? So the increase in mosquito abundance. And as you can see here in Florida, as we already know, very high potential abundance for mosquitoes, right? So the chance of us having vector-borne illness increase is pretty high. And as I said before, those algal blooms that we get as a result of excessive nitrogen runoff, right? So because of our many, golf courses or highly fertilized lawns, that nitrogen running into the water, and because we also in our infinite wisdom decided to manipulate the natural water flow in Florida, it basically caused this situation where we have these huge algal blooms affecting human health, animal health, ecosystem health, and then eventually our water quality, right? Because this is also like Lake Okeechobee, for example, secondary water system or water source rather for South Florida. Okay, that is the end of the climate change lecture. So now you can go on Canvas and take your knowledge check.